Thanks to Caja Negra for giving me the opportunity to moderate this conversation, and before that, for involving me, along with Lourdes and Alejandra, in the translation of Katherine Hayles' book into Spanish. It was precisely while translating and thought that I read Laura Tripaldi for the first time, and I immediately had the impression that they were indeed parallel minds. Both have a scientific background in the same field, in chemistry, which provides a strong foundation for their research into the social and cultural aspects of contemporary technoscience. And their shared commitment to posthumanism and feminism entails for both of them a critique of anthropocentric definitions of intelligence and patriarchal imaginaries of technology, stressing the importance of materiality, embodiment, interdependence, and care. In this sense, parallel minds and thought reveal significant overlaps, but also important differences, summarized by Professor Hayles in one of the emails we exchanged while preparing this dialogue. In her own words, the two projects identify similar problems, like the ecological collapse, and present two different but related strategies for addressing this. For Hayles, widening the scope of cognition, and for Tripaldi, widening the scope of what counts as life. So during this conversation, we'll try to clarify their use of these notions, cognition, life, and many others, their differing positions on material intelligence or agency, their philosophical engagement with new materialisms, their view on the future of technology and especially artificial intelligence, and their ideas about the current role of scientific practice. So first of all, I'm going to introduce these brilliant thinkers, condensing their countless achievements and distinctions, and then we'll start with the dialogue. Katherine Hayles is the Distinguished Research Professor at the University of California in Los Angeles and the James Duke Professor Emerita from Duke University. Her research focuses on the relations of literature, science, and technology in the 20th and 21st century. She's the author of How We Can Posthuman, How We Think and Are Thought, among many others, and her most recent book is Bacteria to AI, published this year. Laura Tripaldi is a transdisciplinary researcher at the interface of science, technology, and speculative thinking. Her research focuses on materiality, exploring its cultural implications and technological futures. She holds a PhD in material science and nanotechnology from the University of Milan Bicocca, and her book Parallel Minds has been translated into multiple languages. She is also the author of two other books, Corpi Ambigui and Gender Tech. So I'd like to start with a broad question. You both offer an expanded definition of intelligence based on the idea that it's neither an attribute exclusive to humans nor necessarily depending on consciousness, but your respective definitions, as well as the entities they include, diverge in significant ways. For Tripaldi, intelligence is a widespread phenomenon that emerges from the way different bodies relate to one another, and can be therefore attributed to materials due to their capacities for self-organization, adaptation, and memory. In contrast, Hayles doesn't speak of intelligence, but of cognition, which she defines as the process of interpreting information in context that connect it with meaning. This allows for the inclusion of biological organisms and technical systems, insofar as they are capable of perceiving, interpreting, responding flexibly, anticipating, and learning, while excluding material processes and inanimate objects. Do you consider that these two approaches are mutually exclusive, or could they, on the contrary, be useful in addressing different issues without requiring a single and univocal definition of intelligence or cognition?
Tony, for that question. Let me say that I very much think that Laura's project and mine are aligned. We both have the same general goals, although, as you know, we use different strategies to reach them. So let me say a little bit about why I chose cognition rather than intelligence. When I wrote Unthought, and also my more recent book, From Bacteria to AI, I wasn't necessarily thinking about the smart matter issue that Laura discusses so well. I was thinking about quantum effects, which are even below where smart matter is, but way above the macro scale. The reason I didn't discuss intelligence is that there are so many competing and sometimes conflicting definitions of it. Cognition seemed a more precise term that I could actually define. You mentioned, Toni, in your introduction, my newer work that identifies 5 criteria for something to count as cognitive. They can be summarized under the acronym CIRL: sensing, interpreting, responding flexibly, anticipating, and learning. I was fascinated when I read Laura's book to think there may be, even at the nanoscale, issues working on with these smart materials. It's possible those materials might actually satisfy these criteria. In my recent book, I talk about minimally cognitive systems, which include plants and microorganisms. But there may be another category of ultra minimal cognitive issues that explain what matter might be. It's all a matter of scale. I certainly understand why Laura would choose the term intelligence, because smart matter is often talked about as intelligent matter. There's a pre-existing usage for that term.
Yeah, well, before replying, I would like to say that it's really a pleasure for me to be in dialogue with Professor Hayles, and I've really enjoyed reading her work over the last few years. It has really inspired me. So thank you to Caja Negra for organizing this, and thank you, Toni, for your questions. Yeah, well, I think that for me, I need to also explain maybe a bit the context in which I wrote this book. I wrote Parallel Minds in 2020 when I was doing my PhD in material science. So I was very much immersed into scientific research, and I wasn't really maybe so familiar in how to navigate the complex terminology that often is part of the debate around the philosophy of mind, right? So I think that for me, choosing the word intelligence was a way to try to capture an intermediate space between human consciousness and just matter as being considered just a passive object of human manipulation. So at the time when I wrote my book, I hadn't read Unthought. I only read it later. Otherwise, I am quite sure that I would have embraced this idea of the cognitive non-conscious, which I think really resonates with what I was trying to capture with my work. So I think my perspective really emerges also from this specific context of science and technology research. And I wanted to, well, foreground 2 aspects. The first one for me that was very important was relationality. So trying to think about intelligence or cognition not as something that is an inherent property of specific beings, but more of something that emerges from the relation between entities. And so this is why I also used this concept of interface, which comes from chemistry, to try to express this idea of emergence in material systems. And I was also, and this is maybe where the title also came from, like Parallel Minds, I was curious of thinking about how, well, different material substrates and different materialities could produce different kinds of cognition. So thinking not only in terms of degrees, but also maybe in terms of diversity. And this is for me, I would say, still a very open question. And it's something that I'm really interested in understanding better. So this tension between universality of function, let's say, and contingency of embodiment.
In Parallel Minds, Tripaldi aligns herself with new materialisms and agential realism, asserting that the relational view of matter that Karen Barat applies to theoretical physics can be extended to also intelligent materials. However, Hayles departs from these currents due to the lack of attention to the different types of material processes and their agential capacities, establishing a distinction between actors and agents, or between cognizers and non-cognizers, that she illustrates with the example of a tornado, which cannot choose to plow through a field rather than devastate a town. However, the materiality of a tornado seems hardly comparable to quarks or nanomaterials. So in this sense, what special properties does matter exhibit at the nanoscale, and which of its behaviors could be considered intelligent?
This is a fascinating topic for me because in Unthought and Elsewhere, I make a strong distinction between actors and agents. I associate agents with physical processes, like a lake evaporating or a rock eroding, and actions with cognitive entities that can make selections and perform interpretations I call actors. I'm reminded here of the criteria of the fuss that historians made of Foucault's idea of a distinct epochs. They said, no, 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 there aren't distinct epochs. There are always gradations in between. And of course, that makes sense. If you take, say, a 50 or 100-year interval, as Foucault did, you can trace a clear difference between Renaissance thinking based on analogy and scientific thinking based on causality. It makes sense that there would be many intervening points between those two. The question is, at what granularity are you looking at this phenomenon? Are you looking at a broad enough scale to see clearly the difference between analogical and causal thinking? Or are you focusing on the transition points, like in an M.C. Escher drawing, where white birds gradually transform into black forms as you move from ground to foreground? And of course, there will always be in these transition zones where it's very hard to say exactly what is happening. In my interpretation, that's where Laura's work falls, in that fascinating transitional region where it's hard to say exactly if something is living or non-living. I take her point that because there are these transitional zones, it's easy to begin deconstructing the difference between living and non-living. But nevertheless, if you take the Foucaultian approach, looking with broader granularity, it is clear that there's a difference between a rock and a bacterium. The bacterium can respond to its environment actively and proactively in a way that a rock cannot. Yes, a rock is subject to physical processes, as is everything on Earth. But the difference is the rock cannot proactively interact with its environment to change its structure or function. As Laura makes clear in her book, smart matter can do exactly that through many self-organizing processes. So I think this is a fascinating question. My critique of some work in new materialism is precisely on that basis, that it doesn't distinguish sharply enough between the rock and the bacterium. I think it's useful to make that distinction, especially since recent work by Longo and Kaufman indicates that there are actually two different temporal regimes in which these entities exist. Their point is that the rock is being subject to physical processes without the ability to proactively relate to the environment, has trajectories that can be diagrammed into phase space. But no biological entity has a trajectory that can be diagrammed into phase space because it's unpredictable. It jumps around as it interacts with its environment, makes selections, performs interpretations, and so forth. So the idea that these processes happen in two distinct temporal regimes is further evidence that it's critical to distinguish between them. That's why I make the distinction between actors and agents.
Yeah, I absolutely think that it's very reasonable to be able to draw distinctions, or at least be able to introduce layers in how matter organizes and responds. And I also agree that often, like, to claim all matter is agential or all matter is intelligent definitely results in a sort of panpsychist indistinction that then is no longer productive, neither speculatively, but also it's not productive when it comes to maybe engineering new technologies and new materials. And so, for example, I think also like the question of scale is very significant. So, for example, Bharat's perspective, for me, when I first encountered it, of course, like being a science student, I was very excited to see fundamental science being used in that way, so speculatively and with such vision, but then also to extend quantum effects beyond a certain scale becomes risky or becomes difficult, right? So for me, when I was writing Parallel Minds, one aspect that was very important to really avoid this collapse into indistinction was to try to develop a toolbox of concepts that maybe could allow me to explain in what specific ways different materials can have agency. So, for example, the concept of scale, of course, is very important. The concept of interface that I mentioned earlier, different kinds of self-organizing systems, so far from equilibrium or homeostatic self-organizing systems, the concept of hysteresis as a form of precognitive memory. So all of these phenomena, which taken by themselves, of course, still belong in the context of physics, at some point, when they become complex enough, clearly they trigger something, or at least if we want to accept that life at some point emerged from inorganic matter, there must be a threshold space where all of these physical phenomena at some point become something else. So maybe this is the space that I was really curious to explore, but not just to make a claim. Really, this is not something that interests me, to make a claim about all matter being, I don't know, intelligent, but more like to think about how a virus is different from a rock, which is different from a galaxy. And these are all sort of non-living systems, but they are very different from each other. And also maybe to think about more practically how to engineer these functions that are more lifelike into our technologies, which does not mean necessarily to replicate life in full, but maybe to mimic some of the functions that can be useful or productive for us in our relationship with technology.
For Hayles, both agency and cognition are distributed across what she calls cognitive assemblages, fluctuating collectives of humans, non-humans, and computational media. While the configuration of an assemblage shifts as condition and context change, adding and removing components, reorganizing connections, and so on, it shouldn't be understood as an amorphous mass. Rather, its interactions are precisely structured as an arrangement of systems, subsystems, and individual actors. In contrast, Tripaldi locates intelligence within a material network characterized by a decentralized and diffuse structure in which a multiplicity of simple mechanisms combine to produce a complex response to the world in which they are immersed. What advantages and limitations does each of these two morphologies and structures, the cognitive assemblage and the material network, offer for unfolding collective intelligence or assigning ethical responsibility?
Again, I think the question of scale is crucial. Laura's approach is very well suited to the nanoscale she's exploring. Most of my work falls into much larger scales, up to human beings and other multicellular organisms. If you think about entities at that scale, it's useful to consider them as individuals. I'm very aware of the work Donna Haraway and others have done, arguing that there are no true individuals, that every multicellular body is a holobiont composed of communities of other organisms. But still, I think that I don't think anyone would deny that humans and other conscious organisms make decisions all the time, go to the store, stay at your desk, and so on. We know that many other mammals do as well. There's increasing evidence that this also applies to plants and microorganisms, that they make decisions as individuals, even though they're interconnected with communities. Work on forest ecology, for example, has shown the importance of both community ties and individual fates. Some phenomena are experienced by individual organisms that communities don't typically experience, like death, extinction, mutation, and other forms of harm. So what we need is a dual approach, one now flourishing in forest ecology that recognizes both the importance of individual selections and interpretations and the importance of community relationality. For those interested in consciousness, there's growing evidence that consciousness is a relational property, that cognition and consciousness both develop through relationship within communities. If an individual were truly raised without any community connections, it's almost certain they would not thrive nor flourish to their full biological capacities.
Yeah, I absolutely would agree that the scale that I'm considering in Parallel Minds is very specific. So I like the concept of cognitive assemblage that you mentioned, Toni, in your question. I think it's extremely powerful, and I don't see that as being in contrast to what I talk about when I speak about materials and their intelligence or cognition, right? It acts on a different scale. So in my book, for example, use the example of the slime mold as a many-headed organism. And of course, like the slime mold is an individual for sure, and it acts in the direction of preserving its own survival, although it is a very special kind of individual, because what it means for the slime mold to be an individual is certainly different to what it means to us. And I was interested in exploring this diversity of slime mold embodiment and what this means for the sort of cognition that it has. So in that case, to solve a complex problem, the slime mold can use this sort of morphological intelligence that does not rely on creating a representation of reality and then solve the problem from there, as we humans would imagine to solve a problem, but it uses its own body and its own shape as a form of computation, if we can use this term, or as a form of intelligence. So this just demonstrates that intelligence can take various forms. So I was also, of course, very interested, for example, in Peter Godfrey Smith's vision of other minds and how the octopus having a different embodiment also manifests a different kind of intelligence. But of course, I think that in terms of upscaling these ideas, like we definitely cannot only rely on distributed delocalization, right? And I think if we take a lesson from biology and how biology upscales its material systems, there is both distribution, right, multicellularity, but there is also like modularity, and different parts of a biological organism serve different functions. So this is also part of that. So modularity and distribution, I see those as like two parts of the solution to the problem. But I also think that the lower scale material complexity and the lower scale sort of distributedness is also non-negotiable to have those higher level functions.
Your redefinition of intelligence also entails a new way of understanding technology. Hayles argues that the coevolution of human and technical cognitions is not only rooted in the origins of our species, what she calls technogenesis, but also extends into our future trajectories, which appear to be increasingly entangled with computational media and AI, or what she calls technosymbiosis. She hopes that acknowledging this ecological reciprocity can contribute to building more open, just, and sustainable futures in the face of the climate crisis. Sharing these environmental concerns, Tripaldi emphasizes that building new materials means inventing new ways of relating to the world, thus rejecting the association of technology with rigid and solid materials in favor of a paradigm shift towards softness, which, in her own words, contributes to a broader ecology of technology, offering paths for sustainable innovation in the face of global ecological challenges. What course should technological development follow to address today's planetary crisis? And since we're dealing with evolutionary processes and complex dynamics, do humans still have any degree of control in shaping these pathways through, let's say, state regulation, ethical design, or technopolitical praxis?
In her book, Laura introduces the idea of life with an F, L-Y-F-E, as a category that might apply to these intermediate materials. That's an idea gaining some momentum in the circles I move in. Sarah Walker, an astrophysicist, has an interesting article arguing that a productive way to think about life genealogically is genealogically. If you do that, you could say, for example, that complex computational systems are of life. They aren't alive, but they belong to the genealogy of life. They wouldn't exist if humans hadn't invented them. At the Berggruen Institute in Los Angeles, where I'm affiliated, there's a lot of interest in planetary sentience and an even larger scale on which to think about intelligence. The systems emerging from life with an F are becoming more tightly integrated with those from life with an I. It's an exciting and productive way to think, and I'm eager to see where it goes.
Yeah, well, in my book, I mean, of course, coming from chemistry, like I am especially attuned with maybe also abiotic phenomena. So in my book, I articulate a position of continuity between the inorganic and the organic, the abiotic and the biotic. But I'm also like, I try to tell the story of how this continuity was constructed also through the history of chemistry and the history of science. So for a long time, of course, like life was considered something unique, something completely separate from the inorganic world. At first, also in terms of composition. So for a long time, chemists believed that organic molecules could not be synthesized in the lab from inorganic materials. And it was only in the 19th century with the synthesis of urea that finally like this rigid boundary was breached, right? So there is the question of composition, so of how do complex biochemical molecules arise. And we know, I would say like this is pretty much a solved question. Like right now we know that biochemical compounds can be found elsewhere outside of Earth. We find them in like meteorites. So clearly those are not exceptional. But the more interesting question, I think, is like the question of structure and also like morphogenesis, right? So how does life, not only in terms of what it is made of, but how is it organized, arise? And so this is why the concept of autopoiesis was very interesting for me when I first encountered it, because I saw that instead of talking about life as only made of specific materials, it started to consider life as being a set of processes. which then, of course, opens an entire space of thinking about life as we don't know it, which means both, of course, like extraterrestrial life or life with a Y, but also maybe synthetic systems that can incorporate certain functions or certain processes from life. And to me, maybe what was especially interesting is like what changes also maybe psychologically or ethically when we shift from thinking about life as something completely unlikely and we start thinking about it as something maybe less exceptional, something that can happen more, right? So we feel maybe less special, but also we feel less alone. And for me, like this is an interesting transition.
Life, alongside intelligence, is another central category in your approach. According to Tripaldi, it's not an extraordinary phenomenon, but one of the many different types of dynamic organization that matter can assume. Drawing on theories such as abiogenesis as well as astrobiology, she advocates for a gradual deconstruction of the category of living matter, whose defining feature would be autopoiesis, that is, the ability of a system to produce and maintain its own organization and structure. However, in Bacteria to AI, Hayles points out some of the limitations of this autopoietic theory, such as its separation between organism and environment, in contrast with Haraway's notion of sympoiesis, and its conflation of life with cognition, which would exclude computational media. She also argues that material processes and biological evolution belong to different temporal regimes, making it necessary to differentiate between them. What are your arguments for either generalizing or restricting the concept of life? Can we understand not only life, but also intelligence or cognition as a planetary scale process or phenomenon?
Thank you for that question, Tony. It's important to both Laura's project and mine. Let me clarify why I think cognition is an important leverage point in these debates. Along the lines Laura mentioned, that it makes us feel less special, but perhaps also less alone. There's a long history of humans patting ourselves on the back for being the most cognitively advanced species on Earth. Cognition has long been the linchpin for confirming human superiority and dominance. It's often been used to justify that dominance. If you broaden the definition of cognition to include other organisms and decouple it from consciousness, then you begin to undermine the rationale for human dominance. We aren't necessarily cognitive superior in every respect. We rely on non-conscious organisms with cognitive functions, like bacteria, all the time, and that leads directly to technogenesis and gene editing. That is why I chose cognition as an important leverage point. It's directly tied to human dominance. I'd be very interested to hear Laura explain how eroding the boundary between life and non-life contributes to the shared goal of finding an alternative framework for thinking about our relationship to other organisms and processes on Earth.
Yeah, well, this is absolutely a crucial question and also a very difficult one. And I absolutely share this commitment of questioning the centrality or the uniqueness of the human in terms of when it is used sort of to reassert dominance towards everything that is not human. For me, well, the concept, as I was reading Professor Hayles' new book, the concept of technosymbiosis really deeply resonated with me. And maybe it's because in Parallel Minds, and also it's something I keep returning to, I wrote a lot about spiders and the relationships that spiders have with their silk, which is, of course, like a non-living material, but it is also, well, more than just a passive tool, more than just a passive instrument. So for the spider silk has been considered to be a sort of extended cognition because the spider has a very limited central nervous system, so a limited cognitive horizon. Silk as a material sort of allows the spider to open up this cognitive horizon through the relationship with this material. And because silk is a very intelligent material, because it can sense its environment, it can adapt to specific stimuli, it can self-organize, it can self-heal, then the cognition of the silk, if we can call it that, and the cognition of the spider sort of become entangled. So even if silk is not living per se, it definitely creates a continuity, which is also a form of coevolution between the spider and the material. And so I've been thinking about this relationship also as a metaphor for imagining what our relationship with the materials that we use and from which we make our technology sort of can be reshaped. So instead of thinking of these materials as just passive things that we can manipulate and shape, can we create a symbiosis with them? Can we co-evolve with them in a way that is productive? So this is sort of the direction that I'm considering. But of course, the question is huge, and yeah, I'm not sure I'm prepared to answer it.
Your scientific training in chemistry explains your shared interest in the philosophy of science and epistemology, and especially the debates surrounding representation. Back in the 90s, at the height of the so-called science wars, Hayles distanced herself from both realism and anti-realism by advocating for a constrained constructivism in which scientific inquiry emerges from the interplay between representation and constraints. However, in Parallel Minds, Tripaldi claims that science has always been a problem of synthesis, not of representation. And while I'm sure that you agree on many points, including your critique of representationalism, I'm interested in the radical novelty introduced by material science and synthetic biology, since in Tripaldi's words, the material under investigation becomes an active participant in the cognitive processes of the science that studies it. Something that Hayles also describes as a technological capture of microcognitions through gene editing and xenobot synthesis. So how do these practices transform our understanding of technoscience, and what possibilities do they open up for humans to interact with material intelligence or cellular and bacterial cognition?
This is an interesting question. When Laura speaks about coevolution, what immediately comes to mind for me is AI. You could debate whether spider silk is cognitive, and I take her point that spider silk co-evolves with a spider. I was fascinated by her detail about combining nanomaterials with spiders to make silk stronger. But if you compare spider silk to AI, there's a massive difference in scale and in coevolutionary capability. I've been working a lot on the evolution of humans and AI, and so have many others, because it's developing so quickly with enormous implications. None of us is fully in control of how this will turn out. The risks and benefits are both enormous. Some say we should stop AI research until we understand the implications better. I don't think that will happen. If one country stops, others will continue. We're on an accelerating trajectory of inventing this powerful technology that will not remain separate from us. It will interpenetrate life at many levels and functions. The likely future, in my view, assuming we don't destroy ourselves first, is increasing hybridization between AI and humans in a wide variety of forms. It's going to change the species. It will change us as individuals and collectively. This isn't new. I argue in my book, How We Think, that technogenesis, the coevolution of humans and technology, has been happening since the beginning of the species. It proceeds in fits and starts, and we're on a clear inflection point that will change rapidly and dramatically. So I'm very interested in how this is going to develop. And I'm also very interested in how we can think about ethical questions in relation to what kind of purchase these have in a highly competitive, highly capitalistic environment.
Yeah, well, to start from maybe from chemistry, that what you mentioned, Tony, about sort of chemistry being an interesting standpoint to start thinking about our relationship with technology. Well, for me, being a chemist, I sort of like my view on science was, of course, not as a process of observing and uncovering nature. Because what is interesting about chemistry is that it not only studies matter, but also creates its own object, right? So chemistry produces the object of its own investigation. And this object that is produced is also not just a passive thing out there, but participates in this dialogue with the scientist. So definitely being a chemist has pushed me to think about science and technology like as a dialogue, as an open process, which definitely resonates with this idea of symbiosis. Another layer, because I absolutely resonate and agree that AI is changing everything, like our cognition. Another side of AI that's really interesting for me is how AI will transform, for example, scientific research and how science will change as AI becomes an active part of it. I've been thinking a lot about this idea. This is a concept that was proposed by Yu Hui, and it's this idea of technodiversity. So Yu Hui has imagined this idea of technodiversity to also propose that while AI is extremely powerful, should we maybe try to cultivate other forms of technology so as to not make technology converge into a single form that then becomes overpowering. So this is a concept that has resonated with me a lot, and I'm still sort of considering it, and I'm thinking whether this is something that we should take into account. So as life thrives on diversity, maybe also technology can thrive on diversity, on the coexistence of different forms and different kinds of technologies. So if we create a world where there is only one sort of dominant species or apex predator, then we also run some risks. Yeah.
Now we'd like to ask each of you to pose a question for the other. Professor Hayles, is there something you would like to ask to Tripaldi?
Well, the question that I sent to Laura and also to you is this. Tony, you were asking about whether she thought that nanomaterials had intentionality. So intentionality is one of the ways I would distinguish between a rock and a bacteria. Increasingly, people like Michael Levin at Tufts are making the argument that intentionality goes all the way down to the cellular level. He co-authored this article with Daniel Dennett called Agents with Agendas, which is arguing that individual cells have intentions, and their intentions are, of course, relatively simple compared to humans. It is to survive. But the idea of wanting to continue its existence is true both for the bacteria and for humans. So it's one of the fundamental principles of the biological spectrum in total. So when Laura says that we should encourage technological diversity, I think that's a really promising and exciting prospect. And I would just say that AI can be a very powerful partner in helping to increase the technological diversity, because it can now be used to encourage other forms of life with an F technological life that we're just beginning to imagine and what might be possible. So I think the big question for me here concerns in intentionality. How does it open onto a whole series of ethical issues, and what are those issues? How can we best guide the intentionality of ourselves and our technology to more flourishing futures?
Well, of course, like the question of whether or at what point do materials start to exhibit intentionality is a very important question. And I absolutely agree that biological life exhibits a striking combination of behaviors that no other material configuration that we know of possesses. So there is absolutely something special about life. So, of course, the position of continuity that I articulate maybe tries to, well, I would say like the smart materials or intelligent materials that we have today definitely do not exhibit intentionality in this sense. But I am curious as to how we can sort of break down this continuing to exist or desire to continue to exist into like some components. And I think that it's very interesting what is happening now in sort of cognitive science, where there is an increasing tendency to look at scalarity and stratification of different processes. I think this is a very interesting perspective, and the work of Michael Levin is definitely fascinating in this sense. So I'm thinking, can we maybe break down intentionality into other more simple or more limited phenomena? So I would think maybe homeostasis, replication or reproduction, and having some kind of metabolism. So I would say these three, which are normally like the three functions that are used to define life. And we have like non-living material. We know of non-living materials that exhibit some combination of these phenomena. So we can, for example, create molecular systems that can self-replicate, or we know of dissipative structures, right? So the work of Ilya Prigozhin has really opened like this whole world of dissipative, far from equilibrium dynamics. So of course, like what if we manage to combine all of these three elements, so homeostasis, replication, and metabolism, we might be able to produce a non-biological system that is both synthetic and that has intentionality, but maybe not. And if not, then maybe we should keep thinking harder as to what provides intentionality to living systems. And it's, for me, like what is exciting is really exploring that space of ambiguity and trying to figure out where this emerges. And I think there is a lot of very interesting work that's being done in this space.
And now, Laura Tripaldi, there's something you would like to ask to Professor Hayles?
Well, my question for Professor Hayles deals with a very interesting for me emerging technology that I've been like increasingly curious about, and this is the world of wetware computing. So I'm sure you're familiar with these emerging technological systems that kind of change the substrate of computational technology from silicon-based structures to new materials that can be either biological materials in like living neurons have been used, but also there is this other world of neuromorphic materials, which are not exactly biological, but can mimic certain functions of biological neurons in a more embodied way compared to silicon-based computers. So my question is really, what do you think about these emerging systems? And do you think that there will be any substantial differences, if we are able to upscale them, which is still, of course, like a very open question, will there be any differences, not only in terms of maybe like quantitative differences of processing efficiency or speed, but also qualitative differences in how they can sort of interact with us?
Well, I won't attempt to speak about wetware possibilities since I don't know much about that area. But I would like to speak about the neuromorphic chips that you mentioned, like the Synapse project at Hewlett-Packard and funded by DARPA and so forth. So the neuromorphic chip is the neuromorphic project is to build a chip that operates on the basis of synapses rather than digital code. Basically, what we have here is a very powerful technology still in its infancy. As I understand it, the inventors of neuromorphic chips are still in the process of trying to invent a language that would allow them to communicate with it. So it's at a very early stage. But what we have here is a fascinating instantiation of analog computing on a digitally constructed substrate. So with AI, what we have is something different, essentially an analog application running on a digital machine. So the digital part of the neuromorphic chip is perhaps the most important part and maybe the biggest part of it. The analogical part of it, which is establishing different parameters for individual neurons, is a self-organizing system, and that's the analog part. So in the whole history of computing, there's been this continual interplay between the analog and the digital. But the neuromorphic chips are distinct in that they've changed that ratio, making the analogical much more important than the digital. Now in the analogical, it's the analogical part that does most of the work in the computation, and the digital substrate is more a manufacturing facility to make possible analogical computation. It really is opening a new history in computational theory and computational practice to go back to analogical computing and to begin exploring its possibilities. So the connection here with the biological world is that if we think about computation as a biological function, for example, in a forest, it's almost entirely analogical. There are only a few isolated examples of digital computation in the biological world. Our synapses, for example, have a form of digitality in that they're either fire, they're on, or they're off, but really it's an analogical system. So the fact that all these different forms of cognition that exist in the biological world are based on analogical computing means that there's a tremendous possibility that it will lead to increased diversity, and I'm sure that will lead to increased functionality as well. It's difficult to say at this point what those increased functionalities might be because it's so early in its evolution. But it just makes sense to me that, of course, it's going to have different functionalities because there is this fundamental difference between digital and analog, digital abstraction and analog computing. The very first thing you do if you're composing a digital program is that you extract your variables of interest into binary code, ultimately with abstraction. With analogical computing, it's not based on that kind of abstraction. It's based on building a model, and the model has the advantage of having the independent variables interacting with each other directly. They're not going through the abstraction of digital code. They're physically interacting with each other within the model. So there are these early forms of computation that are analogical, like mercury tubes, hydraulic computing, so on and so forth. That kind of fell by the wayside, except for specialized applications with the rise of digital computing. And digital computing is very clean because it's built on abstraction. You don't have to worry about all those messy interactions that make the system so complex in an analogical system. I mean, it's one of the kinds of complexity emerging, building up from those interactions, but on a fundamental level, with digital computing, it's very clean and it's very simple. It's 1 or 0, and you build up the logic gates from that. So what if you start from a basis that is not abstract and not that simple, which in fact is far more complex? It just makes sense to me that you are going to get far more complex results. The problem is, how do you engineer that? It's an extremely difficult problem. Life found a way to do that, but now we're trying to do it with our artificial cognition.
Thank you. This was a very interesting response. And I really like this idea of AI as being like an analog function that runs on a digital machine. And I'm also curious to see where this will go.